Okay, we are going to go ahead and get started. So, while I was making this review, I pulled things from the previous reviews that I've done. I pulled some example problems from other exams. And then I also made sure to add this stuff from chapter 15, which is the section on NMR, and some synthesis problems, which was I think it was the last problem on your guys' last exam 3, where it was like, give me the steps to get from this product or starting material to this product. And I didn't think she was going to do a problem like that on your third exam. So that's why I didn't have one on the last review. So that was my bad. But I definitely made sure to include a couple on this one because you'll probably have a few more of those on your final. So with that, I'm gonna go ahead and get started. So going all the way back to chapter 1, hybridization. Just a quick little overview of the sigma bond versus the pi bond. So sigma bond is found in all bond types, and it's going to be in an s orbital. And then single, double, and triple bonds will all have this type of bond. And then the pi bond is only found in multiple bonds, and that is going to be in a p orbital. So in double bonds, there's going to be one pi bond. In triple bonds, there's going to be two. So if we look over here on the side, this first line is a single bond, and it only has a sigma bond in purple. The one right below it is a double bond. We still have our sigma bond in purple, and then our pi bond is above it and below it in gray. And then with the triple bond, we get the sigma bond in the middle, the first pi bond on the top and the bottom, and then the second pi bond on the front and the back side. So then moving on to orbital energy diagrams. These are also going to be called arrows on lines in some of your problems. That's typically how she refers to them. And it's how we show which orbitals our electrons are in, because when we have molecules forming, things are not going to stay just like in an s orbital, in a p orbital. Most of the time we're going to have some hybridization happening, because it's going to make it a little bit more stable. So in this example for nitrogen, we see that traditionally when hydrogen is not, or not hydrogen, nitrogen is not hybridized, this is what it's going to look like. We have our 3 p orbitals with 1 electron each, and then our s orbital will have 2 electrons in it. And then if we hybridize that, we get 4 sp3 hybrid orbitals. One of them has 2 electrons in it, and the other 3 are going to have 1 electron in it. And these 3 that have 1 electron are going to be what is able to bond with other atoms, right? So this is why nitrogen likes to form 3 bonds, because it has 3 sp3 orbitals that are only half full. And then this one with 2 electrons in it is going to be that lone pair that we typically see on nitrogen. Bond angles and shapes of our different type of hybridized orbitals. With sp3, our bond angle is going to be 109.5 degrees, and it has a tetrahedral shape. And that's going to be drawn over here. You'll see that's where we will get typically that wedge and that dash that we have been really accustomed to seeing. With sp2, we get 120-degree bond angles and a trigonal planar shape. And this is just an example of that over here. And then with SP, we get a 180-degree bond angle in a linear shape. And that looks like this, kind of like a little bit of a sunset. So that might help you remember that. And then now we have an example. So this problem says to indicate bond angles around our highlighted atoms. So around this first one right here, does anybody want to answer what our bond angle there would be? Yep, 109.5. Whoa, that is way too big. Okay. 109.5 degrees. Around this second one, what would our bond angle be? Yep, 120. And then around this third one, what would our bond angle be? Yeah, 180. So those are just the 3 different bond angles you need to know and the 3 different shapes that you need to know as well. And then it's to draw hybridized orbital energy diagrams for our highlighted atoms. So looking at this carbon here, would we hybridize that to sp2 or sp3, sp2, or sp? Yeah, sp3. So we're gonna get 4 sp3 orbitals, and it's a carbon, so we're just gonna have 1 electron in each one. Now with carbon 2, which is this one here, would that one be sp3, sp2, or sp? Yes, sp2. So we're going to save the p orbital for that double bond and then hybridize the rest. So we get 3 sp2 orbitals, and those are also going to have 1 electron in them because, again, it's a carbon, and carbons have 4 valence electrons. And then finally, that nitrogen, are we going to be sp3, sp2, or sp there? Yeah, sp. So we'll save 2 p orbitals here. And then sp will have 2 orbitals there as well, but one of those is going to have 2 electrons in it. And then finally, what are the sigma bond orbital overlaps in bonds 1, 2, and 3? So on bond 1, what would be our overlap there? Yeah, sp3, sp2. Or you could do it the other way. You could also write it sp2, sp3. It doesn't matter. With 2, what would that overlap be? Yep, sp2, sp2. And then with 3, what would that overlap be? sp2, sp. Yep, perfect. So something I want to say with this type of thing, I imagine that with hybridization and orbital energy diagrams, I have a feeling that she'll probably do something related to resonance with this. So what I mean by that is she'll draw something like this. Say we have that there, and then this is a nitrogen, and then like this, she'll probably ask you something about a question like this. That way she can knock a couple of things out with one problem. So if you were to see something like this and she's asking like, oh, what is my orbital energy diagram for like nitrogen, for example, what she's wanting you to recognize here is that nitrogen has a lone pair on it, and that lone pair is adjacent to this double bond over here. So because of that, this lone pair of electrons is not going to be in a regular hybridized orbital. It's actually going to be in a p orbital. So if I were to draw the orbital energy diagram for that, I'm going to save actually 2 p orbitals. One of them has 1 electron in them. The other one has 2. And then this nitrogen is actually sp hybridized, even though it only has a double bond on it. So that is an example of a problem that I have a feeling that she's probably going to ask you something like that. So just remember, when you are looking at these, you want to make sure you're paying attention and looking just in case there is resonance on there as well. So do we have any questions about hybridization?
Wait, so for the one that you just showed for the p orbitals, how do you know like one is single and the other one is like double? So you mean like there's three pi bonds?
No, so what this is telling me is just that. So this p orbital with one electron in it is representing the double bond. The p orbital with two electrons in it is representing my lone pair that can participate in resonance. So that's the difference there. If you see a p bond or a pi bond, a p orbital, that has two electrons in it, that means that that lone pair is participating in resonance. And that's the only time really where you'll see a p orbital with two electrons in it.
Oh, okay.
All right. So then if no one has any other questions, we're going to move on to IR spectroscopy. So, just again, a quick overview of IR. Why do we use it? It tells us useful information about our molecule of interest, specifically functional groups. So we do this by looking at the size and location of peaks on the spectrum and comparing them to a chart of known values. So this is a pretty typical chart that you guys will be given. She will give you this chart on your final. You don't have to like memorize them, which is really nice because it's a lot of things, and the one she gives you has even more information than this one. This one is just a very condensed version. She will give you one on the exam, so you don't need to worry about memorizing any of that stuff, which is really great. And the big thing with these is just being able to recognize where certain things traditionally show up. So alcohols are always going to show up in the same spot. Carbonyls are always going to show up in the same spot. sp3 carbon hydrogen bonds are always in the same spot. And so when we look at a spectrum, I think the best way to kind of go about looking at these is to just look at the specific pieces of your spectrum and then trying to make sure, or not make sure, but trying to see if you have certain peaks that are correlated with those different functional groups. So, kind of an example of what I mean when I say that, and what I like to do is I like to split it up so that we have the space above 3000, we have space at 1700, and then 1500. Now remember, she's never going to ask you anything about this region here, because that's a fingerprint region and it starts to get really, really messy and we can't really use it to identify our functional groups all that well. So the only spots you need to pay attention to are going to be the things above that 1500 region. A couple of things that I look for specifically in this region here above 3000 is if I get any big broad stretches or if I have any short kind of staggered peaks there. And there's actually nothing above this 33,000 line here. So that tells me I don't have an alcohol. So no alcohol, no carboxylic acid. And then there's no sp2 carbon hydrogens. So that actually tells me a good amount of information about what else I possibly could have. So I do have a peak here right below 3000, and it's kind of a little bit staggered, but nothing super crazy there. And traditionally when you see something that looks like this, that's just going to be, oops, I did not mean to do that. That's going to be your sp3 carbon hydrogen stretch. And that's not always going to be super helpful just because almost every single molecule will have that. But it's good to know that it is the sp3 carbon hydrogen so you don't think it's something else. And then the other thing that we have here is a carbonyl stretch. So This molecule, really all I know about it is that it has a carbonyl in it and it has sp3 carbon hydrogens. Now, I forgot to do this at the beginning, which was my bad, but really the first thing you should do anytime you're looking at problems like this and you're given your formula for your molecule is you want to find your degrees of unsaturation. So we do number of carbons minus half the number of hydrogens plus 1. So we get 1 degree of unsaturation. So that makes sense for what we see here on this chart. And I'm just going to leave it like that for right now, and then we're going to come back to it because all of these molecules have the same. Sorry, I forgot to take that off. But all of these molecules have the same molecular formula. So really, all I'm looking for is just differences in the peaks and kind of seeing what different functional groups are going to look like. So now if we look at this second one, if I draw my lines up around 3000 and around 17, is that 17? Yeah, around 1700. This is going to be, this one does have something above that 3000 region, and it's really big and it's really broad, and it's going to have a shape that looks more like India rather than like Florida. Oopsies. So this, I would say, if I had to not really take a guess, but if I had to identify this, I would say that this was an alcohol, right? And the other thing I right away noticed is that here in the 1700 region, there's no carbonyl stretch. So I don't have a carbonyl here. But I do have this kind of extra stuff here above 3000. So this I'm going to say is sp2 carbon hydrogens, which is traditionally, I'm going to look something like if we have a double bond and then a hydrogen off on that. And then we also have our traditional stuff down here that is going to be our sp3 carbon hydrogen. And then finally moving on to this last one. Drawing our lines up again. So on this one, we do have a carbonyl. So we've got that carbonyl stretch here. And then if we compare this stretch below 3000 to this one, we notice that this one is a lot bigger. And that's indicative that this is actually going to be an sp3 carbon hydrogen, kind of right next to that aldehyde. So this tells me that this is an aldehyde. So the carbon, like that. So now I know, okay, this one is an aldehyde, this one has an alcohol, and this one kind of just has a carbonyl and an sp3. Now when I go back, I can pay attention a little bit more to my molecular formula. So this only has 1 oxygen in it. So I know that as far as this carbonyl goes, it can't be an ester. It obviously can't be an aldehyde. It doesn't have that bit, and it doesn't have the carboxylic acid spot. So this has to be a ketone. And we can just draw any form of a ketone that we want as long as it has the correct number of carbons, hydrogens, and oxygen. So 1, 2, 3, 4, 5, 6. So I could draw it like that, or I could draw this one like this. Yeah, I think that's it actually. Yeah, that's it for this one. We could have either one of these 2 options. Now if we go down to this one, all right, this one we said doesn't have a carbonyl on it. It has instead a double bond and an alcohol. I mean, those are the two main things that we see here. So we can draw this again in a couple of different ways. We can do it 1, 2, 3, 4, 5, 6, like this, and just put the double bond anywhere in there. It doesn't matter where. It could be where I drew it here. It could be here. It could be going this way. It could be going this way. It doesn't matter. It just has to be somewhere in there. Or we can do it some way where we have our carbon chain and then the alcohol is coming off that way. So it's secondary alcohol instead of a primary one. And then again, we just need to add our double bond in somewhere. So we could put it here, we could put it here, we could put it on the end. Any of those places would be fine. And then now looking at this last one, we said this one's an aldehyde. So it's going to have to either look like 1, 2, 3, 4, 5, 6, like this, or it would have to be something like this. So either one of those two would be fine there. So do we have any questions about doing IR?
For the last one, like I'm kind of confused about aldehydes still. Like the dry structure, not even how you identify it.
Drawing the structure?
Yeah, and it's like it has 1, 2, 3, 4, 5 carbons. Like the bottom that
Yeah,
one that you
I just forgot one. There we go. Yeah, so it's just a matter of when you're doing these, you can draw them whatever way you want as long as it has an aldehyde in it and it has the correct number of carbons and oxygens and hydrogens. So there are a lot of different ways that you could draw these. These are just a couple of examples.
I just like don't get the difference between a ketone and an aldehyde. Like they kind of look similar.
Yeah, they do look really similar. So the difference is going to be that with the ketone, we have a carbon on both sides here. Whereas with an aldehyde, we have a carbon and then a hydrogen on this side. It's not drawn in because remember, we don't have to draw in our hydrogens there because they're assumed. But that is the difference there. And the way I remember the difference between a ketone and an aldehyde is that aldehyde has an H in it and ketone doesn't. So the aldehydes have the hydrogen on one side and the ketones don't. So typically people think that that's a pretty helpful way to remember that. But yeah, does that make sense?
Yeah.
Okay. So now we're gonna move on to resonance. I know this was a big problem area for a lot of people. So I tried to go a little bit more in detail with the stuff like this. But basically, in order to have resonance, we have to have delocalized electrons, and that's going to happen in conjugated pi systems. And a conjugated pi system is just where our electron density is dispersed throughout the molecule instead of just on one atom. It's dispersed across a couple different ones. And conjugated pi systems can either be alternating single double bonds or a lone pair of electrons adjacent to a pi system. So the alternating single double bonds would be something like this, where we get single double, and then lone pair of electrons adjacent to a pi system could be a couple different things. We could do it like this, where we have a lone pair on the nitrogen and it's next to this double bond here. So you could do it like that, or there's a lot of different ways you can have that. But basically, you just need to be able to recognize when we have a lone pair of electrons that is next to a double bond, not on the double bond, but next to it. And you have to have one of these. Oops. You need to have one of these in order to have resonance. Because if you don't have one of these, then there's no way that you can have resonance. So these are the only ways that you can really get it. So rules for resonance. There are some rules and guidelines that we should follow when we're drawing our arrow pushing mechanisms for resonance. The rules, which are things that we cannot break at any point, is that position of the atoms can't change, because if we move atoms, then we're changing the molecule, and that would then be a completely different thing. That'd be a completely different mechanism type of thing. It would be like a reaction rather than just an arrow pushing mechanism. We can only have pi electrons or lone pairs of electrons that can be moved, not sigma electrons. So that's to say that if there's a single bond and you moving those electrons means breaking that bond, then you cannot move those electrons. And then hybridization of atoms can't change. So I can't change something that's sp3 hybridized into something that's sp2 hybridized to make resonance. It has to already be in place before we start. And then guidelines, which are things that we should just try our best to follow, is that we want to minimize formal charges if possible. If we do have formal charges, though, they should follow electronegativity. So a negative charge is better for it to be on like an oxygen or a fluorine or something like that, instead of something that's more positive. And then we also want to try and follow the octet rule. We can get less than 8 electrons, but you can't ever have more than 8 electrons. So that's something to be aware of as well. So onto this example, how many delocalized electrons are in the molecule below? And that's to say, like, how many electrons are actively participating in resonance. Yeah, so we have 4 electrons that are delocalized. And they're going to be these 2 in this double bond, and then this 2 on this oxygen. I kind of tried to trick you guys with this lone pair on the double bond. Remember, it can't be on the double bond. It has to be adjacent. Sometimes you'll have electrons that are on a double bond and adjacent to a double bond. And in that case, they could participate in resonance, but they have to be adjacent, like no matter what. And then draw orbital energy diagrams to illustrate hybridization of oxygen and nitrogen. So this is a problem that I feel like she would probably ask you to do when we move on, like, to our exam. She'll probably have you draw orbital energy diagrams for something like this. So for the nitrogen, it has a double bond, so it's going to be sp2 hybridized. Hold on. So we're gonna have one p orbital with 1 electron in it here. And then we'll have 3 sp2 orbitals, 1 with the lone pair in it, then the other 2 with 1 electron. Now, if we compare that to the oxygen, which the lone pair on the oxygen is participating in resonance, that lone pair is going to be in that p orbital. And then this oxygen is also sp2 hybridized because of that. And one of those sp2 orbitals is going to have 2 electrons and the other 2 will have 1. So this double 2 electrons in the sp2 is the other lone pair that's not participating in the resonance. One of these is this for this bond, one of these is for this bond, and then these 2 electrons in the p orbital are actively participating in our resonance. Does that make sense to everybody? Okay, cool. So then we're gonna move on to acids and bases, which was chapter 3. So quick
Wait,
overview. Sorry,
how
go
do
ahead.
you know like, which like electrons on the oxygen are the ones that are participating?
It doesn't matter. You just pick one of them. So it could be this one or it could be this one. It doesn't matter. It's just you just have to know that only one of them is participating in resonance and the other one's not. But which one is participating in the resonance doesn't matter because this bond is a single bond, so everything is rotating anyways. So these things are not set in their position. This lone pair at one point or another will end up on that side anyways.
What about like the P and the sp2? Like in the P, you put two dashes for O and then one for N.
Yeah, so this is to say that the lone pair on this nitrogen is not participating in resonance, right? Because there's not a double bond adjacent to it. So we'd have to have a double bond here, or like if this was like a carbon over there in order for that lone pair to participate, but that's not the case. So because of that, it can't do anything. It can't move anywhere. It just has to stay where it is. So since it has to stay where it has to stay in that sp2 orbital. And this double bond is going to have one electron from the nitrogen and then one electron from this carbon here that's actually forming that bond. Whereas over here, these electrons are actively moving around, and the way they move is through being inside of p orbitals. So that's why we have to put that lone pair inside of a p orbital.
Could you draw the resonance form, like how we will have to demonstrate that?
Yeah, so that would be something like this, where we have our nitrogen, our hydrogen, our oxygen. And what can happen here is we can have this lone pair on the oxygen push over, and then that's going to put another lone pair on my nitrogen. So what we would end up with is a double bond here, a single bond here, and then my nitrogen would have two lone pairs and then a negative charge. And this oxygen would have a positive charge.
Is that the only way, or is it a different?
For this molecule, this is the only way that we can have the resonance. Sometimes with like rings and stuff like that, if you start on like one part of the ring versus another, you can kind of get different starting points, but you should still have all of the same resonance structures no matter where you start from. But yeah, for this specific example, this is the only resonance form that we get.
Okay, thank you.
Okay. So on to acids and bases. Quick overview of pKa. We use pKa typically to determine acidity of our different solutions, our solvents, or whatever that we're using. And a lower pKa equals a more acidic solution, I guess. So in this example, we predict the direction of each of the reactions. So what we're gonna do is we're gonna look at our acids. So this is our acid. This is considered our acid on this side. This is our acid on this one. This is it on this one. And the way that we can tell is that acids are not going to have negative charges on them. They're either going to have a positive charge or they're going to be neutral. Anything with a negative charge is typically going to act as a base. And also if we look, we'll see that this matches with this one. It's just missing this hydrogen, which is like the definition of an acid, right? It's something that donates hydrogens or accepts electrons. So because it's giving away this hydrogen, that's how we would know that it's an acid. And then we can look over at the chart here and write down our pKa's. So that one's a 25, 4.8, 17, 35, And then 4.8 again on the 17th. And the way that the reaction wants to go is from the stronger base to the weaker base. So that means whichever one has the lower pKa of the two, we're going to go from the stronger one to the weaker one. So that means this reaction would go from the right to the left. The B would go from the left to the right, like normal. And then C would also go from the left to the right, like normal. Does that make sense to everybody?
So from more acidic to less acidic, basically.
Yeah. We're going to go more acidic to less acidic. All right. So then Oreo, which is more like Ari, because that's really what we focused on, was the A, R, and I. Atom is for the A, which is to say which atom has a negative charge in our conjugate base, and size and electronegativity matter. So if we look at H2SE versus H2O, our conjugate bases here would be HSE with the negative charge on the selenium there versus our negative charge on an oxygen here in the OH minus. Selenium is bigger than oxygen. It's further down. They're in the same column, but it's further down the periodic table. So because of that, this is going to be more acidic. With resonance, it's just distribution of our negative charge through resonance stabilizes our conjugate base. So more resonance structures equals more acidic because our conjugate base would be more stable. So that acid is more likely to give away its hydrogen. And then with induction, that is strictly electronegativity of stuff that is on like the acid. So for example, we'd get, this is actually not, hold on. What I meant to do here is say we have CH2 bonded to OH, and then this one has a fluorine on it versus CH3OH, right? So in our conjugate bases, with this one, we get our negative charge on that oxygen. Same, we get the negative charge on this one. And the way that we determine which one is more acidic is by looking at this fluorine here. So this fluorine is extremely, extremely electronegative. So it's going to kind of pull this negative charge and distribute my electrons around my molecule, which again makes it more stable, makes it more likely to give away its electrons. So that's because fluorine is more electronegative. All right. So do those three things make sense to everybody?
Did the thing that you erased like was just incorrect in general? Why did you erase it?
No, it wasn't incorrect. It was just I feel like it didn't illustrate what I really wanted you to pay attention to, which is if we have the same thing, so the same like body, right? This is like generally the same as this, but this has a fluorine on it and this one doesn't. That's really how you would see it if you looked at like you saw that on an exam. It would be more likely to be something like this versus like this instead of the way that I drew it. What I had was not incorrect. It's just I feel like this is more what you would need to worry about. And I was going to change that before I posted the worksheet. I just forgot. Okay. So, any other questions about that stuff? Okay. So then we are going to look at this example here, and this is a pretty heavy example. So it says phenol has a pKa equal to 10. 4-hydroxybenzaldehyde has a pKa equal to 7.3. Draw resonance forms of conjugate base of both and explain why for hydroxybenzaldehyde is more acidic. So we want to explain why it's more acidic. And our acidic hydrogen is underlined. So to start off here, we're gonna draw out our conjugate base. Then we can start doing resonance. So this oxygen is going to have 3 lone pairs. One of them can push down. Okay. And when it pushes down, we will get a double bond here. Our oxygen will still have 2 lone pairs on it. And then this bond will push up. So we get 2 electrons there. And then the rest of our molecule is the same. Then we can get it so that this pushes down and this pushes up. See. So that would look like this. Then we could get, so this lone pair pushes down, this one pushes up. And then our final resonance structure here would be if this electron pair pushes down and then this one goes back up. So that brings us back to our starting point where we have this and then our oxygen has 3 electron pairs on it. So in total we have 4 resonance structures here. Now if we do the same thing for the bottom one, we'll see that we get 3 electron pairs on that oxygen. It starts out very, very similarly. But what's going to change is that when we actually are doing our arrow pushing, we have this extra oxygen on here now, so it's going to look a little bit different. So we'll start with this lone pair pushing down, so we get a double bond there, and then this double bond pushing up, so that we get something like this. Then we are going to get, so this electron pair pushes down and this one pushes up. And we get our lone pair there. And I'm also, I just realized I forgot to put negative charges with all of these. So, okay. Now what we can have happen is we can have this lone pair push down like this, and then this one push up. So that's gonna look something like this, where we now have our negative charge there. We have a double bond there. It'll look like this. Then we can go from this position here. Instead of it pushing down, we can also have it push over. I just realized I forgot to draw that. That's my bad. So then we get double bond there. And the lone pair here. And then our final structure will be when we get back to where we started. So we have, oops, this. So we can see that there is an additional resonance structure right here that the phenol does not have. So because of that, that is why we have this lower pKa with the 4-hydroxybenzaldehyde, because we have an extra resonance structure with the negative charge on oxygen. So that is what's going to give us more acidity. How does oxygen regain the double bond? Which, oh, like, right here? Yeah, so this is kind of an extra, I guess a better way to kind of do this would be, like if we showed, okay, this is pushing back up, and then this is pushing over here. You could do it like that. But yeah, basically we just have those electrons pushing back down, and then our electrons are moving over to right here. All right, so does anybody have questions about this example?
So we're basically trying to get back to the normal form by like jumping back and forth, or
Yep, exactly. You want to get back to whatever you start with here. You should be able to get back to that by moving your electrons around with the arrows. And that should be your goal when you're looking at these, is getting back to your starting point. Okay. So then we're going to move on to alkanes and cycloalkanes, which was chapter 4. So a big part of this chapter was Newman projections. And the main thing I want to talk about with Newman projections is looking at eclipsed versus staggered. So the main thing with this is that eclipsed Newman projections are always going to be higher in energy. And that's because of steric hindrance. And so opposite of that, staggered ones are always going to be lower in energy because they have more space. So that's a really important thing to be able to recognize, especially when you're doing conformational analysis. And when we do conformational analysis, we're basically just looking at all the arrangements of atoms in a Newman projection and comparing our energy levels. So if we do a conformational analysis for this molecule here, we're going to start by, well, I'm going to start by redrawing it off to the side here in a Newman projection. Now, I know this is something that a lot of people really struggle with, being able to kind of go from the sawhorse to the Newman projection. So what I want you to think about when you're going from sawhorse to Newman projection, or from Newman projection to sawhorse, is grabbing your molecule. And for this example, like what I'm saying, I'm going to do from like sawhorse to Newman projection, just because that's what we have to do. You're like pretending you're physically grabbing your molecule and you're turning it 90 degrees. That way you're looking at this bond here. You can actually sight down that bond. I mean, we're just going to rotate it 90 degrees. And when we do that, we'll get bromine on the front carbon, chlorine off to the side, and then fluorine off to the side there. And then the back carbon will have chlorine, bromine, and CH3. And then next thing we want to do is make sure we identify which of our atoms are the biggest on each carbon. So bromine is the biggest one on all three of these, or both of them, out of all three. So what we want to start with when we do our conformational analysis is we want to start by drawing it. So we are in our highest energy conformer. So that's going to be where both of our bromines are staggered or not staggered, eclipsed in front of each other. Then we can leave the front carbon the same, right? Because the bromine on the front carbon didn't move. And then on the back one, we're just rotating it 60 degrees so that my CH3 is here and my chlorine is here. Then
Wait, could you show how you even got the first one?
yeah, so the way that I got the first one was just like this one right here.
Yeah.
Yeah, so what I did was I don't have my model with me right now, unfortunately. But what I did was it's easier if you have a model to kind of visualize this, but if once you do it enough, you can just do it without using a model. But you're grabbing the sawhorse, right? I'm grabbing it from carbon 1, which is right here, and carbon 2, and I'm rotating it 90 degrees. So pretend like I'm rotating this over here. And when I do that, that back carbon is flattening out so that the chlorine is on the top, the bromine just rotated to the side. So that's why it's on this side. And then the CH3 again rotates off to the other side. So it ends up right here. And then this front carbon, we have a similar thing. We're rotating it this way, right? The bromine stays on the top. The chlorine is going to be the same place as the bromine because those are both on wedges. So it's going to be right next to it. And then this CH3 is going to be next to the fluorine because those are both on dashes. So they have to be right in front of each other. They're in the same spot.
So are the carbons just always labeled? So it's 1, 2, and then whatever's like on one side is 1, like
Yeah,
in
so
front.
this carbon is the same. This carbon number 1. This is carbon number 1 on the front. And then carbon number 2 is this carbon in the back. And we're just looking down the bond. So it's like if we're looking at it from here and looking at it straight down. Does that help?
Yeah, I think so.
Okay. So then the next thing we want to do is just go through and rotate everything 60 degrees at a time. So we'll start with 0 degrees there. Then we're going to leave our front carbon the same every single time. Chlorine. And I'm just going to right away do this so that I don't have to redraw it a bunch of times. But our front carbon stays the same. We're rotating it 60 degrees clockwise. So the bromine is now over here. CH3 is there. And our chlorine is off to the side there. Then we are going to rotate it another 60 degrees so that we get our front carbon the same. Our chlorine here at the top, our bromine off to the side, and CH3 here. Then we rotate it 60 more degrees this way, and that's going to give me chlorine here, bromine here, CH3 here. Then we rotate it 60 more degrees so that we get our CH3 up at the top, our chlorine here on the bottom, and our bromine here. And then finally, we'll do 60 more degrees that way so that we get CH3 here, chlorine here, and bromine here. Okay. And this is 180, 300. This is 120, and this is 240. So now we have everything drawn out. And the next thing we want to do is recognize our highest energy and our lowest energy conformer. So I already said we started with this one. This one is number 1. So I'm going to put a 1 next to it. And now with the lowest energy, it has to be out of these 3 because these are all staggered, and staggered will always be less, have less energy than anything that's eclipsed. And then of these 3, the one with the lowest energy is going to be the one where my 2 largest groups, which are again my bromines, are completely opposite to each other. So that's going to be this one right here. And if you start with the highest energy conformer like you're supposed to, your lowest energy one is always going to be at 180 degrees. So now I know this is my lowest energy, so we're going to put that one at number 6. Now we can look, of the lowest 3, we can figure out which one's 5 and which one's 4. So in this one, we have our bromine next to a bromine and a chlorine. And in this one, we have our bromine next to a bromine and a methyl group. Now up here, it told me that I'm supposed to assume that the methyl group is bigger than the chlorine. So that means when my bromine is next to this methyl as compared to a chlorine, this one is going to be higher in energy than that one. And then if I'm looking at the 3 that are eclipsed, I already have number 1, right? So now we're looking at these 2, which one's 2 and which one's 3. This one, I have my bromine next to a chlorine, and this one I have my bromine next to a methyl group. And we already said the methyl group is bigger than the chlorine. So that means that this one has higher energy than this one. So now I have all of these ranked, and all I have to do is go to my chart and draw out where they're supposed to be. So 180 is the lowest, and then 0 degrees is the highest. So 1, 2, 3. 1, 2, 3, 4, 5, 6. So this one will start here. And then 360 is going to be the same level as 0. Then we have 240 at number 2. So we'll put that there.
Why is the 360 same level as 0?
Because 360 degrees is the same as 0 degrees, right? Because it's a circle. So 0 degrees is the same as 360 degrees. And I think she wants you to draw 360 from what I remember. So that's why I put it on there. But I think if you drew it with just up to 300, it would be fine. I think she just does that typically to make sure you get back to your starting point.
So if you draw the 360, it'll be the same as the 0? Okay.
All right. And then number 3 was at 120. So 120 is the third line. And then 4 is 300. And 5 is 60. So now all we have to do is connect all of these lines the best that you can. It doesn't even have to be that nice. And this would be a good answer for this type of problem. Any questions about this stuff?
I'm still confused on how you rotate them though. Like which degree, and which one eclipses with which.
Like what, like over here where I'm rotating it?
Yeah.
Yeah, so that's just when we do confirmational analysis. She said that the way she wants us to do it is to start with our highest energy, which we did, and then just rotate it 60 degrees clockwise. So I
So
rotated this
this energy, we make that up, like not make that up, but like we try to eclipse it, like with the I don't get it.
with the energy.
Now, like, how do you know? I understand why the first one is the highest energy, but how'd you even get there?
How did I get here?
Yeah.
Yeah, because since the bromines are the biggest things on both carbons, because out of fluorine, chlorine, and bromine, bromine's the biggest because it's the furthest down our periodic table. So it's the biggest. So that means it's going to be our highest energy thing. And then on the back one, we're looking at chlorine, methyl, and bromine. And of those three, bromine is the biggest as well. And it tells me this up here too, that bromine is the biggest of all of those. So I'm assuming that that's also the biggest. I'm not even assuming, but it tells me that it's the biggest. So because of that, the highest energy thing is going to be when those two are right next in front of each other, because that
So,
means that they're going to be hitting each other a lot. There's a lot of steric hindrance there. So that's how we know what our highest energy thing. It's always what the two biggest things are eclipsed in front of each other.
so the highest energy is only always at zero because they're eclipsed, and like we kind of draw it ourselves to make it
Yeah.
seem like it's highest. Okay.
Yeah. They won't typically tell you like, oh, this is your highest energy one. You kind of have to figure that out for yourself.
But it will always be the first one though, right?
Yeah, for this class it will. And I don't think um I mean most of the time when you're doing confirmational analysis, it will be like that. Yeah, it is about size, not electronegativity. So we definitely want to make sure that we keep that separate. And it's kind of hard with this class because sometimes electronegativity is what matters and sometimes size is what matters. But with confirmational analysis, we're looking at the size, not the electronegativity. All right. So then, did anyone have any other questions about this? All right. So then, a quick overview of cyclohexanes. Basically, this is the chair conformations. And important things about this is that our most stable conformation is when the larger groups are equatorial. And then when we're looking at cis versus trans, I like to think about it as if two things are cis, that means they're on the same side of our chair conformation. So I'll draw this out. I didn't draw it out just because I didn't want to take up a whole nother page just to like draw them out. But basically, if we're drawing this, everything that goes down, I'm considering one side of the cyclohexane, and everything that goes up, I'm considering another side. So when things are cis, they both need to be going up. And then this is cis, and then when we look at, oops. Ooh, this is really bad. If we're looking at, actually, I'm gonna do it the same. Hold on. That's why I was doing it that way. That way we can compare them. Um, one is going up, one is going down. So this is trans. I thought more stable cis is equatorial and more stable trans is axial. More stable cis is equatorial and more stable trans is axial. So not necessarily just because we can have things that are cis like this where one's equatorial and one's axial, but we can also have it where it's like this, where we have one going up, this one also going up. And this is cis, and then this is also trans, where we would get this one going down and this one going up. So it depends exactly where your substituents are on your ring, what's going to be more stable, right? Because if we're looking at this one versus this one is the more stable because this one has the option for both of my things to be equatorial. And then if we're looking at both of these, this one's more stable because this one has the option for both of my things to be equatorial. And the only thing that I changed was I moved my stuff over one carbon. That's all I did. So you really just have to pay attention to where things are on your ring. And I do recommend you draw that stuff out just so you're not making mistakes or anything and you can actually see where stuff is on that ring.
I
Would you
have a
explain
question.
Oh, sorry.
Oh, you're good. I'm confused on the trans one. You said because they're both equatorial, but those are axial. So I think I'm missing something.
Yeah, so they're right now they are axial, but if I do a chair flip, oh my god, this is so bad. If I do a chair flip, then when I do that, this carbon becomes this carbon, right? And now it's equatorial. Hold on. Going down. And then this carbon is this carbon. And now that one is axial going up.
Okay, so when you said
Equatorial
like
going
the
up, sorry.
option to be equatorial, you just meant like if you flip the chair.
Yeah.
Okay, sorry, that makes sense.
Yeah,
But
no,
I
you're
guess
good.
I thought that like if, for example, if she asks like for cis, which one is more stable, you would pick the chair form where they're equatorial. But if she asks which trans is more stable, you would pick when they can both be axial, I thought.
No, we're always more stable is always going to be the one where we have more groups equatorial.
Oh, okay, that's what I thought, but there was a question on an exam that, well, I'll go back and find it, but I thought that it wanted it to be axial, like that made it more stable, and I'm trying to figure out why that would be, but I'll have to go find it.
Yeah, from what I know, and from what she's always said in the past, is that whatever's equatorial or whichever one has more things equatorial is the more stable one.
Okay. Okay, that's what I was originally thinking. So, all right, thanks.
All
Would you
right.
go it's like axial and equatorial again?
Yeah, so axial is just when we have stuff that's going straight up and down. Kind of like when you think of an axis like of a planet, like say like planet Earth, right? Axial goes straight up and down through the middle of the planet. And equatorial is going to be where it goes out to the side. So like if that kind of you can think of it as like the equator. The equator goes all the way around the middle. But it's horizontal. whereas axial is straight up and down vertical. So that's where we can kind of see like this is axial, whereas this is equatorial because it's going out horizontal. Okay. So now I'm going to move on to stereochemistry, which was chapter 5. So this is kind of where we talked a little bit about chirality and what is chiral versus what is achiral. Achiral means that it's a symmetrical molecule attached to two of the same thing. And chiral means that it's asymmetric and attached to 4 different things. So when the molecule is flipped, spatial arrangement changes. And that goes into absolute configuration, which is R versus S. And with R versus S, at this point, you should be relatively comfortable with assigning R and S. And some terms that you need to know is enantiomer, diastereomer, and then meso. So enantiomers are when our configuration flips completely. So that would be like if we're looking at something that's originally RR, an enantiomer of that would be something that is SS. Diastereomers would be where we have something that's RR, and now it's RS. And then meso is where we have a line of symmetry. So basically what you need to know about meso is typically our number of diastereomers is going to be 2 to the n power, with n being our number of chiral centers. And when something's meso, it's 2n minus 1. So we just get one less option for the diastereomers. Does that make sense to everybody? Okay. So then example 7 says to assign absolute configuration to all chiral carbons in the molecule below. So first thing, obviously you need to figure out which carbons are chiral. And from what I see, this one's chiral, this one's chiral, and this one's chiral. So those are our 3 that we're going to be focusing on. And then if we look at this first one, which I'm going to say is this one all the way over to the left, we have a hydrogen going backwards, right? So that's going to be our 4 group. Bromine is going to be our 1 group because it has the highest atomic number. And then between this carbon and this carbon is bonded to carbon, carbon, hydrogen. This carbon's bonded to carbon, hydrogen, hydrogen. So that means that this one's number 3 and this one is number 2. And then we just draw a little arrow. 1, 2, 3. Hydrogen's in the back. So this carbon is going to be R. And then the next one is going to be this one here in the middle. So this one has a hydrogen coming forward. And this is our 4 group. Then this is carbon, carbon, hydrogen. This one's carbon, hydrogen, hydrogen, and then this one is also carbon, hydrogen, hydrogen. So this one is automatically number 1. These 2 are the same though. So then we have to go 1 step further to see what else these are bonded to. So this one is carbon, hydrogen, hydrogen. And then this one over here is going to be carbon, carbon.
Альбо закрой, а!
Okay, so then between those 2 now, carbon, carbon, nitrogen takes precedence over carbon, hydrogen, hydrogen. So this one's going to be 2, and then this one's going to be, this one's going to be 3 right here. So then that one we get 1, 2, 3 this way, which would be R, but our hydrogen's in the front, so we say it's not R. It's actually S. And then last, we'll look at this one all the way on the right. This one, our number one group is going to be this nitrogen. And then we look at what we're bonded to. So this one's carbon, hydrogen, hydrogen. This one's hydrogen, hydrogen, hydrogen. So this one's automatically number 4. And then this one is oxygen, oxygen, carbon. So this one is 2. And this one is 3. Now with this one, you'll notice that our 4 group is in the plane of the paper, so we can't just do, oh, it's R, or it's S, or it's not R, it's not S. We have to redraw it, rotating it. So I'm going to hold group 3 still. I'm going to rotate it. So 4 is now in the back, which puts group number 2 on a wedge. And then number 1 ends up down here. Then we can go through and do our arrow. This one is S. So this carbon here, oops, this one is also S. Does that make sense to everybody?
Wait, so why did you have to redraw it?
Because my number 4 group wasn't on a wedge or a dash. So for us to be able to just look at where 1, 2, and 3 are, 4 has to be either on a wedge, so I can just assign it normally, or it has to be on a dash, so I can assign it normally, or a wedge, so I say it's not. Whatever we get, when it's in the plane of the paper, I can't do that. I have to rotate it so that either my 4 group's in the back or it's on the wedge. So that's something really important that you guys need to make sure you are able to do, is rotate that molecule, because that is something that will come up, especially if you are taking like OChem 2 and you're going to have to take that ACS final. They will have problems on there where your 4 group is on in the plane of the paper and you need to rotate it.
So you rotated by changing like the big wedge to a dash?
So it's not really that. What I want you to think about when you're doing it is you're actually rotating the things. So like I want you to think like I'm moving this one here, this one here, and number 4 is now going over there. Does that make sense?
So you said like the 4th will be on the dash because it's on a straight line?
No, I'm moving it so that it's on the dash. It doesn't just like, I'm not just switching things because I like want to or because I can. I'm actually physically looking at my molecule and I'm rotating the bond. So I'm holding this here still, and then I'm rotating my other 3 so that they're switching, not really switching places, but they're moving. So that's where number 4, I want it to be on the dash, right? So I'm moving it to where 2 is, which means 2 has to go where 1 is on the wedge, and then 1 moves to where 4 is because I'm rotating them.
Oh, okay.
All right. So I know someone said that they wanted to go over miso really quickly. Let me see. Let me try and come up with an example really quick of something that is miso. So I'll do, yeah, I'll do this. And then, yeah, we'll just leave it like that. We'll leave it simple for right now. So this molecule has a line of symmetry right through the middle. So because of that, it has a meso structure. So right now, if I were to like assign the actual absolute configuration, we would get, this is 3. This is 3 also. 2. Oops. 1, 2, 3. This one is R. This one's 1. This one's 2. 1, 2, 3. 1, 2. This one is S. So right now, the way that it is, this is RS. I think I did that right. 1, 2, 3. S. 1, 2, 3. R. Yeah. So right now it's RS. And basically what you need to know is that even if I were to flip-flop this, like do a little pancake flip, so that now it is like this. And I get my hydrogens here on a wedge. This is 3, 2, 1, 1, 2, 3. This one is still R. Oops. Hold on. 1, 2, 3. S. 1, 2, 3. R. So basically, what miso is to say is that these two, if I fold them in half, they're going to be exactly the same. So rather than having something that's SR and RS, these kind of communicate the same thing because it's a miso structure. So I have something that's RR, I have something that's SS, but I only have one that's RS or SR because that RS structure has a line of symmetry and it's going to be the same either way. Because also, this is, we'll call this carbon 1 and this carbon 2. When I flip flop it, this is carbon 1 and this is carbon 2. So basically, it's more like this. They're both RS. So it's the same thing, essentially, is what the miso tells us. Does that help? Okay. Cool. So then now I'll just very briefly just talk about Fisher projections. I don't think you'll have this on your final, but it's just important to know that this, when you see this is what you should be envisioning in your mind, is something like this. And when you see something like this, you can assign absolute configurations to the stuff inside of there. And it's the same, exactly the same as it is with any other type of molecule. Okay, so then on to substitution and elimination reactions. I'm skipping chapter 6 just because all the stuff in there was covered in like the chapters after it. So like in order for you to understand chapter 7 and chapter 8, you have to understand chapter 6. So we should understand all that stuff in chapter 6, kind of by default. But chapter 7 was about substitution and elimination reactions. And we had 4 that we really cared about, which
Wait, could you go over the Fisher projections?
like what do you mean like by go over?
Like assign them.
I'll do one just because we don't have that much time, because I know Dr. Kimbrough has her review session right after this. So I'll do one. I'm not going to do the whole thing, but the rest of them would be exactly the same. So I'll do this one here on the bottom. Here. So what you're going to want to do is assign your carbons just how like you normally would. This is going to be my number 4 group over here. Then this is my number 1 group because it's directly bonded to an oxygen. So I guess kind of a better way to have that would be OH like that. And then we're comparing this carbon to this carbon here on the bottom. So this carbon is bonded to carbon, carbon, hydrogen. This one's bonded to carbon. Oops. Oxygen, oxygen, hydrogen. Yeah. So this one's 2. This one's 3. You're going 1, 2, 3. Which would be S, but you're 4 groups in the back. So this is actually not S. It's R.
Wouldn't the COOH be the first group though, because there's 2 oxygens?
No, so because it's directly bonded to a carbon. And that's what we're looking at first. Because the oxygen takes precedence over that carbon. So I'll also redraw this so that we see, like, yes, it's bonded to that carbon. Or yes, it's bonded to 2 oxygens, the carbon is. But the first thing it's bonded to is a carbon. And oxygen takes precedence over that carbon. Okay. So back to substitution and elimination reactions. This is the stuff that we just had on that exam. So we have our SN2 reactions, E2 reactions, SN1 reactions, and E1 reactions. So with these, SN2 reactions are going to be one-step concerted mechanisms, which are going to look like this. An important thing to remember here is you get inversion of configuration. E2 reactions are going to also be one-step concerted mechanisms. But instead of us just switching things out, we're going to actually get a double bond to form here. And important things about this is you have to have anti-periplanar geometry, and there has to be a strong base to pull off the hydrogen or the deuterium, because you can pull off hydrogens or deuteriums with an E2 reaction. With SN1 reactions, it's a 2-step first order reaction, and it competes with E1 most of the time. And important things here is that we get scrambled stereochemistry, and carbocation rearrangements are extremely likely. So that is something that you really want to make sure you pay attention to. For this specific example, we start with a bromine on a tertiary carbon, so we're not going to get carbocation rearrangement there, just because a tertiary carbocation is already extremely stable. So we're not going to get anything with it there, but I do have 2 different examples of ways this can happen, because we can either have it come in with a nucleophile, and the nucleophile just stays as it is, or we can have it come in with a nucleophile that has a hydrogen on it that will actually leave. So depending on what your nucleophile is, it could either look like this, where it just goes in and then stays how it is, or it can go in and then there's an extra step where we have a hydrogen leaving. And then with E1, again, 2 steps first order, and this competes with SN1, except on tertiary carbons with sulfuric acid. So with the same, we're starting with the same molecule here. If we were to get E1 instead of SN1, our carbocation is going to be in the same spot, but now we're just looking at hydrogens on adjacent carbons. So this carbon has hydrogen on it. This carbon also has a hydrogen on it. And then this one over here. So a strong base will come in, pull those off, and then our double bond will form in between where the hydrogen was bonded and the carbocation. So this one will form here. This one will form here. And then this one will form here in the middle. And again, with these, carbocation rearrangements are likely. And then when we're determining which one is the most stable, it's the one that's the most substituted. So this is going to be the most stable one because it's bonded to 1. Oopsies. It's bonded to 1, 2, 3 carbons, whereas this one's only bonded to 2, and this one's also only bonded to 2. So do we have any questions about those 4 reactions?
I have a question. How do you know if something, like, how do you predict that you're gonna get something that's racemic?
Yes. So with something being racemic, that is going to go to if we have scrambled stereochemistry or not. So some of our mechanisms are going to be very stereoselective. Like if we look at SN2, it's very, very stereoselective because we're going to get inversion of configuration. So everything very specifically has to be on a wedge or on a dash. So with that one, we only have one product. We're not going to get the other option, the other enantiomer, basically, because racemic just tells us that we get both enantiomers. With this one, with SN1, right here we have a carbocation form, right? And this carbocation doesn't have a side that it favors. So when my nucleophile comes in and attacks, it's going to do it from the front side, but it's also going to do it from the back side. So we're going to get products where it looks like this. Oops. Where our nucleophile is here and then our carbon's on the back. But then we're also going to get ones where our nucleophile is on the back and this methyl group's in the front. So the racemic just tells us that we're getting both of these. And typically, I mean, I always write on my review sheets when we get something that's racemic, I'll write out that you get scrambled stereochemistry. So here it says scrambled stereochemistry. You'll notice that none of these other ones say that. And then if we come down here to where we have stereoselectivity on the addition reactions, and this we'll talk about this too in a little bit. But this one says scrambled, this one says scrambled, this one says scrambled. So that means that either we're gonna get racemic if we have one chiral center, or plus enantiomer if we have more than one chiral center.
I'm sorry, can you say that last sentence one more time? It was just a little bit a lot for me.
Yeah, no, you're fine. So if we're looking at our final product and we have only one chiral center, then we can just say racemic. But if we're looking at our final product and we have two or more chiral centers, then we have to say plus enantiomer. We can no longer say racemic because racemic says that I'm getting both R and S at all my chiral centers. And if I only have one, then that's fine because that's exactly what I want. I want both R and S at that chiral center. But if I'm looking at something with two chiral centers, then I don't want R, 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 S, S, R, and S, S. I only want the two enantiomers. So that's why we have to say plus enantiomer instead of racemic.
Okay, thank you. That makes so much sense.
Yeah. All right, and then just onto this table, this infamous table. This table is your best friend, and I said this last time, but if you can kind of just memorize it, at least for like maybe look at it right before your exam and then write it on your exam right before, like as soon as you get it, write it down. That way you don't have to like go into your brain every single time to like try and figure out what type of reaction is going to happen, and you can just look at a table. And it's not like cheating or anything because you actually wrote it down yourself. So I highly recommend doing that. I think this table at this point, hopefully everybody knows how to read it. If not, though, you can ask me to go over it in a little bit more detail. But if not, if everyone does feel good about this, then we're just gonna move on to our addition reactions.
I have another question, if you don't mind.
Yeah, go ahead.
Before you move on to addition reactions, for these other ones, how do we know like what the products are gonna be?
Yeah.
Like,
So
for example, like, oh, sorry, you can go
go
ahead.
ahead. Finish your question. Finish your question.
Well, like I was doing like a practice problem the other night, and I realized we kind of only have the products memorized for the addition ones, but we're asked what the products are going to be for these other ones. too, right?
Yeah, so like on the name that product section.
Yes.
Yeah, so what you'll have to do with those is this is where using this table would come in really handy. You would look at whatever your reagents are. So say it tells you it's OH minus, and then you look, oh, it's a primary like my leaving group's on a primary carbon. Then I can say, okay, this is my nucleophile. This is where my leaving group is. I'm gonna get E2 and SN2, but SN2 is gonna be my major product there. And then you would just draw that out. And so sometimes she'll say draw major product only. And in that case, you would only want to draw your SN2. Sometimes she'll say draw all of them. So she said draw all of them. Then you would draw SN2 and you would draw E2 as well. And then just specify that SN2 is major there.
Well, I guess I'm confused because, like, for example, on the exam 3 key, it's like 1D or whatever, but it's basically like it has a molecule with bromine coming off of it and a methyl group, and it's like a ring, and it says that the reagents are just like heat, and then the CH3 CH2OH. So like on the right column right there.
Mm-hmm.
But
Yes.
I don't know what's gonna come off like instead of the bromine. You know what I mean? Like,
Yeah.
do I have to
So
know that?
what's gonna happen in that one is your bromine is the one that's going to leave. Because I mean the bromine is the good leaving group there. Like CH3 is not a very good leaving group. And those are our only options really, is that methyl or that bromine. And so that bromine is still going to be our leaving group. And then when we go in with our nucleophile, which is that CH3, CH2OH, it's just gonna replace it very similarly. And that's where we would just have racemic or plus enantiomer. You could do either one, and that's why on the key she has it written like racemic or plus enantiomer. You can have either one. But yeah, basically with those, I know specifically with the weak base, weak nucleophile column, this one's a little bit more confusing just because there are some exceptions to this not applicable that it says. So like our exceptions would be on a primary carbon if it's resonance stabilized by either being benzylic or allylic, or on the secondary one if we can rearrange to a tertiary carbon, then that SN2 or SN1, sorry, will still happen. I hope that was a
Okay.
lot. I hope that helped a little bit. Maybe not.
No, it was thorough. Thank you.
Okay. So then, does anyone have any other questions about SN, or I guess substitution or elimination reactions? We'll just say it that way. How you approached or suggest that we approach the name that product and name that reagent questions like the ones that she posted on the exam. Yeah, so when you're looking at name that product, the first thing that you definitely want to do is look at what you're starting with and then look at the reagents. I know that's kind of like straightforward. But at this point, you should have reagents, at least for all of your addition, you should have all of your reagents memorized. Because you need to be able to know what happens when they're there, but you also need to be able to write them out. So you should have those memorized. And then what I always did, because with reagents for addition reactions, very specific products are going to form. So I would always do those ones first. And then with the substitution and elimination ones, I would go through, figure out exactly what the nucleophile is going to be. Is it a strong base, strong nucleophile, weak base, weak nucleophile, kind of that type of stuff. And then I'll look at, okay, is it on a tertiary carbon, secondary carbon, primary carbon? And then kind of look back through that table to decide what my product is going to look like. And that's why you need to know how to use this table, like mentally, if you don't want to write it out, or by looking at it, if you do decide to write it out on your exam, but you also need to know the mechanisms for the substitution elimination reactions pretty well. That way you can just go through, and once you decide, oh, it's SN2, you know exactly what's going to happen. And then with name the reagent questions, I like to compare my starting material with my product. I like to see exactly what changed. And then from there, you can typically see, oh yeah, I remember this reaction does that. And then you can just write in the reagents that you know perform that type of reaction. All right. Okay. So then with addition reactions, this is all from this table. It is a lot of information, but I think that the best way to look at this table and understand what happens is to start with the same starting material every single time, and then look at the differences when I use different reagents. That makes it extremely, extremely clear why these different types of reactions are like valuable and how we can use them to our advantage. And it becomes really, really handy when you're doing synthesis problems. So the only thing I'll say about this table is that you need to know mechanisms for the ones that are highlighted. And those are pretty straightforward. Again, I'm not going to go through them specifically today because they are in the review from last time. And they also are in the PPP that we did. So if you specifically want me to go through that, I would recommend watching that because I did do it on there. So then this is where our last exam kind of ended in terms of material. And then this next example, this is gonna be one of the harder things you guys are ever gonna have to do in yeah, so these are the hardest types of questions you're gonna have to do because you kind of have to be creative. And in order for you to be able to do them successfully, you have to know every single reaction that you're learning. Because if you don't know one, then you can get stuck and then you can't finish the problem. So, I think that this first one is a little bit more straightforward than the second one. I tried to make sure it was a little more forgiving. And someone just asked if we can go over the last question in the exam that needs 4 types of addition. Did you mean like a synthesis problem like this where you're having to use different reactions to get to your product, or? Okay, yeah. Okay, cool. So this should hopefully help with that. Because I did try to incorporate a couple of these into the review this time. So you're kind of have to change your way of thinking when you look at these problems, because they are very different from anything I'm sure you guys have ever really had to do. And the way that I like to think about them is I like to think how I like to look backwards. So I'll look at my product and see how could I get a product like that. But then I also like to think, is there a way for me to get from my starting material to something that will then give me my product? So I'm kind of thinking about it 2 different ways. simultaneously to try and puzzle piece this stuff together. So the first thing that I'm seeing here is that, okay, I'm not adding anything on here. All I'm doing is moving my double bond. And so this obviously has to be some sort of elimination reaction that's happening here, because that's the only way we can form a double bond. And something else has to be happening here for me to be able to get to a place where I can actually get here. So initially I'm thinking, okay, what are the different types of addition reactions I have? If we look back up here, I don't think we would need to do, or it's not possible really to do a dihydroxylation. We're not adding any halogens or anything, because this adds 2 halogens. This adds a halogen and an OH. And remember, when we're doing elimination, we're only pulling off one leaving group. So it's not possible for me to do any of these 4, because I'm adding 2 things that would have to be removed, and that doesn't really make sense. And now I also couldn't really do catalytic hydrogenation, because all that adds is 2 hydrogens, and that's not really very valuable to me, because I need to be able to have a leaving group on there. And then now we're left with these 4 reactions kind of up here. So we could either add a hydrogen and a leaving group, which seems like it could work, or we can add an OH and a hydrogen. So it's also important to note, when you're looking at these, there are a couple different ways that you can do them. So now if we look back at this, I could do this a couple different ways. The way that I originally had it written out, and I'm going to make this a little smaller, is that we're going to go from this, and we're going to add H2O and H+, which is going to give me, oops, sorry, it's going to give me 2 different things. Because this reaction is carbocation rearrangements are very likely. So I'm going to get 2 things here. I'm going to get this, or I'm going to get this. And this is not helpful. So this product is the one that I care about. And that is something else that I'll say. Sometimes you'll get reactions that will give you multiple things. When you're doing a synthesis, she doesn't care if you get multiple things from this reaction. So what I mean by that is I get 2 products here, but it doesn't really matter. As long as I get to something, I don't even really need to pay attention to what else is there. So I can then, from here, I'm then able to get to my final product if I add concentrated sulfuric acid. And this is the reason that I did this, is because, you know, you could do it this way, but another way you could do it, I think, is if you add HBr or HCl, you can get here, and then from there, to get to my product, I could use some sort of strong base like potassium tributoxide. So these problems are going to have multiple correct answers. And so all you need to worry about is whatever you have written, if it makes sense and you could get to your final product, then you will be fine, because there are so many ways to get to the correct answer, especially once you start doing problems that are super long and have a lot of steps to them. So someone asked, can't H2SO4 do the same thing for the second way? So we actually can't use concentrated sulfuric acid here, just because for us to be able to use concentrated sulfuric acid for an elimination reaction, we have to have a tertiary alcohol. And since this is not a tertiary alcohol, we wouldn't be able to use it here.
Oh, where did like the double bond go and where did the OH come from? Because like you made that up.
This?
Yeah, and the double bond from that.
Yeah, so what happens here is and this kind of goes back to the mechanism for it. We're adding hydrogen first to this double bond. It's going to add over here. We're going to get a carbocation there. Now, I'm saying that there's carbocation rearrangement, and that's how I'm going to get my carbocation here so that my OH can go in right there. So that's what's happening, and that's what these reagents are telling me. Does that make sense?
Yeah.
Okay. So then, does anybody have any other questions about this first one?
Sorry, I'm confused about how you went straight from H2SO4 to that double bond being made. Because when I did it, I used H2SO4 to get the OH off because I thought that's all it could do. And then I used CH3OH to do an E1 reaction. So how did you go straight from H2SO4 to that double bond?
So you're saying, oh yeah. Okay, yes. I see what you're saying. Yeah, so you would need to, wait, hold on, actually. No, I don't think you would need 2 steps. Because, give me just 1 second to check my notes. I'm pretty sure you can do it with just this, but I could very much be wrong. So let me just make sure before I speak. Okay. Yeah, you can do it with just H2SO4. You don't need anything else with it, because if we look at the mechanism, my H2SO4 is going to dissociate into these hydrogen ions. We're going to get into this, which is now a good leaving group. And it's just going to spontaneously kind of leave. Then we'll get our carbocation here. And then what's going to happen, instead of like us having to use anything else, I'm pretty sure from what I have in my notes that this can then act, this H2O that comes off over here. So now we have H2O, right? That's that. This will then pull off a hydrogen. So we have a hydrogen here, that'll pull that off. And that's how we can get up there.
Thank you.
Potassium tetrohydroxide can work for the first way. No, so potassium tetrohydroxide wouldn't work for this step here because this OH is a really bad leaving group. And in order for that to work, it has to be a good leaving group. So that's the benefit of using this sulfuric acid, is that it makes the OH a good leaving group. Okay. So then onto this next one. This one has an is a little bit harder. But I'm just gonna walk through it. I can only think of one way to do this for specific reaction, but if you can think of another way, then you're probably correct. Like I said, you do have to be quite creative here. But if I start this one and I decide that I want to kind of form a double bond right here, just because it looks like I'm adding something on this carbon, right? We're adding this group here. The only way that I can add stuff is if I start with a double bond. So that's what I'm going to do first, is make a double bond. Oops. I don't know why I did that. So we're using potassium tetrohydroxide to do an E2 reaction. I'm going to form a double bond in between these carbons here. Then I'm like, okay, what can I add on there now that's going to be a good leaving group? I only really know one way, at least that from what the reactions you guys know right now, that we could do that, and that would be to add hydrogen and bromine. And this is a Markovnikov regioselective reaction. So my bromine's going to add on my more substituted carbon. Then now all I have to worry about is getting from here to here, because I'm in a pretty good spot at this point. So the way that I would do that is just do CH3OH and heat. That way we would get an SN1 reaction. So does anybody have questions about that?
I did it a little differently, and I don't know if it's right. I did like the first step as doing OH minus as an nucleophile and an aprotic solvent to push it to SN2 to make Br leave and be replaced by OH. And then I did H2SO4 concentrated to make OH leave and have there be a carbocation, which would then rearrange. And then I did CH3OH to make that carbocation have an SN1.
So you did, let me just make sure you got to this first step and then you added acid to do an elimination.
Yeah.
And then what was your last step?
Oh, sorry. So yeah, I did OH and then I did H2SO4, but I didn't know that you could make that go straight to the double bond. So instead I did CH3OH to like resolve the carbocation.
So from here, you did CH3OH?
I did H2SO4 and then
H2SO4 and then CH3OH. Oh, okay, I see. Right, because we said afterwards that you can just use the sulfuric acid, right?
Yeah, I didn't know. So yeah.
Yeah, no, you're good. You're good with that. And then what did you do after that?
CH3OH was the last thing I did because I had the carbocation in the bottom right, and then I did CH3OH, and then I had the 1H leave because the oxygen had a positive charge. And then
Okay.
Yeah.
Yes, I see. So you did instead of just doing that to do the elimination, it was kind of you had a carbocation form here,
Yeah.
and
Because
then you had the CH3OH.
yeah.
Okay. That way you got that OCH3 here.
Mhm.
Okay. So your thinking there was really good. Okay? Super, super good. But I don't think this specifically would work
Okay.
just because when we do use the sulfuric acid here to get rid of this OH and make it a good leaving group, we automatically get like a double bond forming there.
Mhm.
So yeah, you were definitely on the right path though with this. And if there was a way, and like say there was a way to get from here to here, and you'll probably learn a reaction for that next semester if I remember correctly, then you could go with that and you would be good to go. But the only thing that I would say is just that we don't have a way to get from this up here to this.
Mhm.
So that's where we would kind of have to go back and like rethink and see if there's another way that we can get to our final product.
Okay. Thank you.
That was really good thinking though. All right. So then the few of you that are still here, we'll just go over really quickly hydrogen and carbon-13 NMR. So what is NMR? NMR is a way to look at a compound and determine the arrangement of the atoms. It uses spin active nuclei in hydrogen and carbon-13 in a magnetic field to do this. I'm gonna be very real with you guys. You don't really need to know that stuff for the exam. She's not gonna really ask you for it. I think it's just helpful for like understanding and stuff. And I do know they ask about it in lab. With hydrogen NMR, important things that the spectra will tell us is the chemical shift will tell us how close a hydrogen is to an electronegative atom. Integration values will tell us how many hydrogens are in a specific chemical environment. And then splitting pattern will tell us how many hydrogens are adjacent to the hydrogen that peak represents. So if we look at either one of these, both of these are things you can use. I included them both because I know some people have preferences. I like to look at this one because it's very visual and similar to where I would look at the spectra and see things on there. But this one, a lot of people like it too because it's has a little bit more things that it shows you. So whichever one you prefer, you can use either one and you'll get to this. You should be able to get to the same place. And then with carbon-13 NMR, important things that it tells us is our number of carbons, and if we have symmetry or not. The chemical shift tells us how close the carbon is to electronegative elements, and then how many hydrogens are bonded to the carbon using depth, which is this here. So anytime she gives you a carbon-13 spectra, she'll also give you the depth directly underneath it. And then this one, again, you have either this more visual one up on the top, or you have this one down on the bottom, which has them written out in kind of like a list format. So I included one example on here, which just says, based on the spectra below and the given molecular formula, propose a reasonable structure. So first step, when we look at these, find our degrees of unsaturation. So 8 minus 5 plus 1 equals 4 degrees of unsaturation, which is good to know. Now, I'm not sure exactly yet when I look at this where those are going to be at. But there is a way that I can find out from my IR spectrum. So I'm going to do the same thing that I always do. Draw my line up there, draw a line around 1700, and then draw my line at 1500. So first thing I'm saying is that I do have an alcohol peak here. So that's important to know. That's where my oxygen's coming from an alcohol. Then I have my traditional sp3 carbon hydrogens. And then right here, I have a peak that could be two different things. So I don't have the spectrum right here. On the exam, obviously you would have it, so you can look at it very easily. But this could either be sp2 carbon hydrogens in a double bond like this, or it could be carbon hydrogens in an aromatic ring. So if we look at an aromatic ring, it could be hydrogens on there, which are also going to be sp2, but they're just in a ring, so they have something else that will tell us specifically. The way that I can tell the difference between those is that aromatic carbon hydrogens will have a peak right at 1600. So this peak here tells me that it's a carbon-carbon aromatic bond. So this tells me now I know I have an aromatic ring. That's where my 4 degrees of unsaturation come from. So from looking at my IR, I see, okay, I have an aromatic ring and I have an alcohol. Now I can look at my hydrogen NMR. Why did that get erased? My hydrogen NMR and my carbon NMR to see how my atoms are actually arranged. So when I look at the hydrogen NMR, these 5 hydrogens are in the aromatic region. So that tells me that my ring is monosubstituted. So I just have one thing on there. And then from these, all I'm going to note for right now is that these are both triplets. This is a singlet. And this singlet is most likely going to be from that alcohol. So I'm going to cautiously say that this singlet is because of the hydrogen on that oxygen. And then these 2 triplets, I'm not going to specifically say where they are or not are yet. I'm going to figure that out by looking at my depth and my carbon-13. So when I look at my carbon-13, in my depth, this carbon doesn't show up on the depth 90 or the depth 135. So that means it's a carbon with no hydrogens on it, which fits with me saying that my ring is monosubstituted, because when we look at a ring, this carbon has no hydrogens on it. So that makes sense. Then we have 3 peaks here, 2 kind of in the same spot, and then 1 down here at the bottom. Those are probably going to be from these 3 different carbon environments. So we're going to say this is A, B, C. These are probably A and B, and then this one is C. There's no way to really tell that, but that's just to kind of make sure we're getting all of our bases kind of figured out. And then we have these 2 down here. They don't show up on the depth 90, and they show up upside down on my depth 135. So that tells me that these are both CH2 groups. And then I'm also noticing that this one is shifted further downfield. So it's next to something that is pretty electronegative. So if I kind of look up here and I look at my carbon-13 one and I see stuff, let's see what range is that in. It's about 60, a little higher than 60. That could either be a carbon-nitrogen, which we don't have any nitrogens, a carbon-carbon triple bond, which we don't have that either because we don't have any more degrees of unsaturation, or a carbon-oxygen bond, which does make sense. So, I have 2 carbons here that are triplets on this one. I guess I don't know, these are carbons, probably. But 2 hydrogens that are being split into triplets by 2 other hydrogens. So this is where I'm going to kind of take a leap of faith, trust my knowledge, and make a guess about what my structure looks like. Now I'm going to just double check that this would actually make sense. So this is 2 hydrogens in the same chemical environment being split by 2 other hydrogens into a triplet. In this one, we have the same thing. We have 2 hydrogens in the same chemical environment being split by 2 other ones into a triplet. And then these hydrogens are right next to an oxygen, so they're probably shifted down over here. These ones are in between, or they're next to an aromatic ring, so they're also going to be shifted up a little bit, but not as far as this one. And then that also adds up with what we have over here with our 2 CH2 groups. So based on all of this stuff, I would say that this is a reasonable structure based on everything that it gave me. Does anybody have any questions about that? All right. So then if nobody has any questions, then that is going to be the end of this review session today. Thank you guys for coming. Thank you for a great semester. Unfortunately, if you or sorry, no, let me reword this. If you are taking organic chemistry 2 with Dr. Kimbrough, unfortunately, I'm not going to be a learning assistant for her next semester, but I am going to be tutoring in the Learning Resource Center. So if you do want help with your stuff at any point in organic chemistry 2, you can always come to those tutoring hours once I decide when they're going to be. But yeah. Any last minute questions before we end this session?
Could you send me the link to Kimbrough's review session?
Yes. I will send that to you right now.
Okay, thanks.
Mm-hmm.